So let's look at these questions. Ibuprofen and paracetamol are pain relief drugs. So this is the structures of ibuprofen. So we have a benzene ring. We also have a carboxylic acid group somewhere here, COOH. This is paracetamol. So paracetamol, we have this particular part. This is called amide. C double bond O linked to NH. This is amide, and this part is like phenol. So let's look at A. Ibuprofen and paracetamol both contains the aryl benzene functional group. So that means they have benzene. So they have benzene as the structure. Name the other functional groups present in each molecule. So for ibuprofen, you may mention carboxylic acid, as we discussed here. Okay, C double bond OH. C double bond O and OH is carboxylic acid. So we put it here. Carboxylic acid. Paracetamol. Paracetamol, you can put this part. The C double bond O and NH. This part is called amide. Okay, now we move on. Ibuprofen contains a chiral center and shows stereoisomerism. So the chiral center here is the chiral carbon. That means the carbon stick to 4 different groups. So state what is meant by the term chiral center. So carbon that has 4 different groups. So that is chiral center. So draw the 2 stereoisomers of ibuprofen. So of course, to draw out the ibuprofen's mirror images. So first of all, we need to find out. We need to find out where is the chiral center. So if you can see, it is actually this particular carbon. So where, let's say I put a star there. So this is a chiral center because this carbon is stick to 4 different groups. The first one is C double bond O, OH. The second one is here, CH3. The third one is these particular structures, the one with benzene ring and side chain. And the fourth one is the hydrogen. So there are 4 different groups. So now we have to draw out the mirror images. So let's say on top, I put the structures with the benzene ring. Put it on top. Okay, so over here. Okay, so this is the first one. Okay, let's say the next one I put hydrogens. So hydrogen on the left, now it goes to the right. And then next one I put, let's say I put CH3. So CH3 on the right, now it goes to the left. Okay, the last one I put COOH. Okay, so COOH on the left. Now it moved to the, oops, sorry, this one, the right moved to the left. Now COOH moved to the, from the left here, now it moved to the right, COOH. Okay, so this is the mirror images. Now let's move on. Next part. Draw the structures of the organics products when ibuprofen and paracetamol react separately with lithium aluminum hydride. So this is a reducing agent. So the reducing agents will change carboxylic acid back to alcohol. Okay, we change carboxylic acid back to alcohol. So basically, we have to take it like this. if there is a C double bond O and lithium aluminum hydride, we'll change it to OH and H. Okay, so you can see two things. The double bond O change to single bond and then take H. The carbon take one more H. So altogether, two hydrogens are added to the structures over here. Okay, so if we look at these questions, so we have the C double bond O somewhere around here. Okay, likewise, paracetamol have C double bond O around here. So we have to work on that to change it to COH and H. Okay, so in that case, right, you may feel like if I follow that idea, so this thing should become the C double bond O should become COH and H. Okay, should become OH and H. Okay, we don't draw the H. Okay, but the thing is, if this is the structures, then we have to say that this is two hydroxy group or two alcohol group. Okay, two alcohol group, which is not stable. So they will release one of the hydrogens. So sorry, they will release one of the OH group, and they will form. Okay, let's see first. Two hydrogens here. I have to change it to CH2 then. CH2. Okay, so this part should change to CH2, something like this. Okay, CH2. CH2. Okay, let's see first. CH2. Okay, maybe I put it in this way. It is carboxylic acid. So you just bear in mind, carboxylic acid after reductions, it will become primary alcohol. Okay, carboxylic acid will change to primary alcohol. So we have to take it in that way. So if like that, okay. So that means this theory is not supposed to be like this. Okay, let me correct a bit first. It's not like this. C double bond O. Okay, so correction for the theory part. C double bond O. So it should become C H. Should be like that, and then it makes sense. Okay? It makes sense. So the lithium aluminum hydride should change the C double bond O to CH2. Okay, then it makes sense. Okay, so ibuprofen, well, the C double bond O here. So this particular part, it becomes CH2. CH2 we just draw like that only. Okay, so okay, now let's put the answer here. So this is the first structures. Likewise, over here, you can see the C double bond O over here. The C double bond O, you change to CH2, like what we discussed just now. Okay, so after doing so, our structure should be OH, NH. Okay, so here becomes CH2. The C double bond O becomes CH2. So we just leave it like that, and we settle and by doing something like this. Okay, so Remember, the C double bond O becomes CH2, and that's all. Now we look at part D. A student carry out some reactions with solutions of ibuprofen and paracetamol using reagents D and E, and the following results were obtained. Take means a reaction took place. So for reagent D, we have an unknown reagent here. Ibuprofens react, paracetamol, no. Okay, so if this is the case, so you should think of the carboxylic acid. Carboxylic acid react with a reagent D, but this one, paracetamol, doesn't react with reagent D. Okay, so you may think of carboxylic acid react with, for example, carbonate, salt. So let's say sodium carbonate. So Na2CO3, where the carboxylic acid react with the metal carbonate, and then they form salt and carbon dioxide and water. But this amide do not react with carbonate. This phenol does not react with carbonate as well. So carbonate will be the reagents. And then for E, as you can see, E is where paracetamol react with reagent E, but ibuprofen no. Okay, so for these situations, you may think of the reaction of phenol. For example, phenol react with bromine. So to form a white precipitate, for example, this is what we have gone through. But this one, no. Okay, no, because it's not reactive. So not reactive. So this one react with bromine, and this one, no. Okay, so we can take that as our answer for this case. So if that is the situations, so we can put BR2 here. BR2. Okay, so if you're wondering why phenol react with bromine, but this one no, because phenol is ring activated. It is reactive. But this benzene ring is not ring activated. Okay, it is some more ring deactivated. Okay, ring deactivated. So it doesn't react with bromine. Now let's move on. Part 2. Give the structures of the organic product formed when reagent D react with ibuprofen. Okay, so we have to draw out the structures when carbonate react with the carboxylic acid. Okay, so they form salt. So we have to draw out the salt actually. So this part no change. Remain. Okay, salt. Now part 3. Give the structures of the organic products formed when reagent E react with paracetamol. So we put bromine. So bromines will add to the para and auto position. But you can see here, this position has been taken. So we can only add here and here. Okay? We can only add to position 2 and position 6. 2 and 6. Position 4 cannot. Position 4 has been occupied. Okay? So bromine can be added to position 2 and 6. So we draw the structures. OH remain. NH. Double bond O. Okay, bromine come here and here. Okay, so this page. One of the steps in the manufacture of ibuprofen is shown. Okay, so let's see here. We have X react with CH3COCl with aluminum chloride. Okay, so you have to know that this is acylation. So acylation is where the COCH3 add to the benzene ring, COCH3. So this is the part CO, here is CH3. So write an equation for the reactions between CH3COCl and aluminum chloride. Okay, so we write the equation for the reaction here. So to write the equation, of course, we have to we have to know that aluminum chloride is the catalyst. So the role of the catalyst here is to take the Cl. Take the Cl so that CH3CO become the electrophile, which is a positive ion. So we want to do something like that. So we write CH3COCl. This is acyl chloride. React with aluminum chloride. So the catalyst will take the chlorines to form this, and after losing Cl, so this one will be CH3CO positive charge, which is electrophile. And the electrophile, of course, if you still remember the mechanism, it will stick to the benzene ring. Now part 2, complete the mechanism for the conversion of X into Y. X into Y. Include all necessary curly arrows, any relevant dipoles and charges. Okay, so that means we have to write down the electrophilic substitutions. Okay, so over here, we already have the first equation in E part 1, which produce the electrophile. So I draw out the electrophile straight away, CH3CO positive. So this is the electrophile. So the electrons you go and from the benzene ring to the carbons with positive charge, and then they form a new bond. So initially there are 6 pi electrons in the benzene ring. So when they form a new covalent bond with the electrophile here, so 2 of the electrons from the 6 electrons in the benzene ring, the 6 pi electron, 2 has been taken to form the covalent bond, and because of that, the benzene ring is positively charged for temporarily. Okay, it's positively charged, and then for temporarily the hydrogen is still there, and after that these hydrogens will be removed, and when they're removed, the bonding electron is going back to the ring to re-establish the 6 pi electron. Okay, so let's say I draw it down here. Okay, the hydrogen ion is released at the end. So that is the whole mechanisms. And part 3, name the mechanisms in part 2. So we can call this electrophilic substitutions. Okay, electrophilic substitution. So settle.